हेलो फ्रेंड्स, तो राना अकेडमी में आपका स्वागत है। हमने स्टार्ट की है 12th क्लास की एनसीईआरटी की केमिस्ट्री की सीरीज़, वन शॉर्ट सीरीज़। तो स्टार्ट करते हैं। द सॉलिड स्टेट हमारा फर्स्ट यूनिट है। लेट्स स्टार्ट। From our earlier studies, we know that liquids and gases are called fluids because of their ability to flow. The fluidity in both of these states is due to the fact that the molecules are free to move about. On the contrary, the constituent particles in solids have fixed positions and can only oscillate about their mean positions. This explains the rigidity in solids. These properties depend upon the nature of constituent particles and the binding forces operating between them. The correlation between structure and properties helps in the discovery of the new solid materials with the desired properties. For example, carbon nanotubules. Now there are new materials that have no potential than aluminium and have more conductive property than copper. Such materials may play an expanding role in future development of science and society. Some other in future and high are high temperature second superconductors, magnetic materials, biodegradable polymers for the for packing for packaging, biocompliant solids for surgical implants, etc. Thus the study of this state becomes more important in the present scenario. In this unit we shall discuss the different possible arrangement of particles resulting in several types of structures and explore why different arrangements of structural units lend different properties of solids. We will also learn how these properties get modified due to the structural imperfections or by the presence of impurities in minute amounts. In class 11, you have learned that matter can exist in three states, namely solid, liquid, and gases, under a given set of conditions of temperature and pressure. Which of these would be the most stable state of given substance depends upon the net effect of two opposing factors. These are intermolecular forces which tend to keep molecules or atoms or ions closer, and the thermal energy which tends to keep them apart by making them move faster at sufficiently low temperature. The thermal energy is low and intermolecular forces bring them so close that they cling to one another and occupy fixed positions. They so close that they about their mean positions and the substance exists in solid state. The following are the definite mass, volume, and shape. They have definite mass, volume, and shape. Sorry. Intermolecular distances are short. Intermolecular forces are strong. Their constituent particles, atoms, molecules, or ions have fixed positions and can only oscillate from about their mean positions. They are incompressible and rigid. Solids can be classified as crystalline and amorphous on the basis of the nature of the order present in the arrangement of their constituent particles. A crystalline solid usually consists of large number of small crystals, as each of them having a definite characteristic geometrical shape. The arrangement of constituent particles, atoms, molecules, or ions in a crystal arrangement of constituent particles, atoms, molecules, and ions in a crystal order and repetitive in three dimensions. If we observe the pattern in the one region of the crystal, we can predict accurately the position of particles. In any other region of the crystal, however far they may be from the place of observation. Thus, crystal has a long range order, which means that of observation. This crystal has a long range order, which means that there is a regular pattern of arrangement of particles which repeats itself. periodically over the entire crystal. Sodium chloride and quartz are typical examples of crystalline solids. Glass, rubber, and many plastics do not form crystals, where whence their liquid solidity solidify and cooling. These are called amorphous, meaning no form. The arrangement of constituent particles, atoms, molecules, and ions in such a solid has only short range order. In such an arrangement, a regular and periodically repeating pattern is observed over short distances only. A regular patterns arrangement is disordered. The structures of quartz crystalline and quartz glass amorphous are shown in figure 1.1a and b respectively. While the two structures are almost identical, yet in the case of amorphous quartz glass there is no long range order. The structure of amorphous solids is similar to that of liquids due to the differences in the arrangement of the constituent particles. The two types of solids differ in their properties. Crystalline solids have a sharp melting point. At a characteristic temperature, they melt abruptly and become liquid. On the other hand, amorphous solids soften, melt, and start flowing over the range of temperature and can be molded and blown into various shapes. Amorphous solids have the same structural features as liquids and are conventionally regarded as extremely viscous liquids. They may become crystalline at some temperature. Some glass objects from ancient civilizations are found to become milky in appearance because of some crystalline like liquids. Amorphous solids have a tendency to flow through very slowly. Therefore, sometimes these are called pseudo solids and super cooled liquids. Amorphous solids are isotropic in nature. Their properties, such as mechanical strength, refractive index, and electrical conductivity, etc., are same in all directions. It is because there is no long range order in them, and arrangement of particles is not definite along all the directions. Hence, the overall arrangement becomes equivalent in all directions. Therefore, the value of any physical property would be some same along any direction. Crystalline solids are anisotropic in nature, that is, some of their physical properties like electrical resistance of refractive index show different values when measured along different directions in the same crystals. Now, this arises from different arrangements of particles in different directions. This is illustrated in figure 1.2. This figure shows a simple two-dimensional pattern of arrangement of two kinds of atoms. Mechanical properties such as resistance to shearing or stress might be quite different in two directions indicated in the figure. Deformation in CD direction displaces row which has two different types of atoms, while in AB direction rows made of one type of atoms are displaced. The differences between the crystalline solids and amorphous solids are summarized in table 1.1. Table 1.1 distinction between crystalline and amorphous solid. Besides crystalline and amorphous solids, there are some solids which apparently appear amorphous but have microcrystalline structures. These are called polycrystalline solids. Metals often occur in polycrystalline conditions. Individual crystals are randomly oriented so as a metallic sample may appear to be isotropic even through a single crystal is anisotropic. Anisotropic Anisotropous solids are useful materials. Glass, rubber, and plastics find many applications in our daily lives. Amorphous silicon is one of the best photovoltaic material available for conversion of sunlight into electricity. In section 1.2, we have learned about amorphous substances and that they have only short range order. However, most of the solid substances are crystalline in nature. For example, all the metallic elements like iron, copper, and silver, non-metallic elements like sulfur, phosphorus, and iodine, and compounds like sodium chloride, zinc sulfide, and naphthalene are from crystalline solids. Crystalline solids can be classified in various ways. The method depends upon the purpose in hand. Here we will classify crystalline solids constituent particles together. These are van der Waals forces, ionic bonds, covalent bonds, metallic bonds. On the basis, crystalline solids are classified into four categories: wise, molecular, ionic, metallic, covalent solids. Let us now learn about these categories. Molecules are the constituent particles of molecular solids. These are further subdivided into the following categories: non-polar molecules, solids. They comprise either atoms, for example, argon and helium, on the molecules formed by non-polar covalent bonds, for example H2Cl2 and I2. And the solids, the atoms or molecules are held by weak dispersion forces of London forces, about which you have learnt in class 11. Now these solids are soft and non-conductors of electricity. They have low melting points and usually in liquids and gaseous state at room temperature and pressure. Polar molecular solids, the molecules and of substances like HCl, SO2, etc. are formed by polar covalent bonds. The molecules in such solids are held together by relatively stronger dipole-dipole interactions. These solids are soft and non-conductors of electricity. Their melting points are higher than those of non-polar molecular solids, yet most of these are gases or liquids under room temperature and pressure. Solid SO2 and solid NH3 are some examples of such solids. Hydrogen are bonded molecular solids. The molecules of such solids contain polar covalent bonds between hydrogen and F O or N atoms. A strong hydrogen bonding binds molecules of such solids like H2O ice. They are non-conductors of electricity. Generally, they are volatile liquids of soft solids under room temperature and pressure. Ionic solids. Ions are the constituent particles of ionic solids. Such solids are formed by the three-dimensional arrangements of cations and anions bound by strong Coulombic electrostatic forces. These solids are hard and brittle in nature. They have high melting and boiling points. Since the ions are not free to move about, they are electrical insulators in the solid state. However, in the molten state and when dissolved in water, the ions become free and move about and they conduct electricity. Metallic solids. Metals are orderly collection of positive ions surrounded by and held together by C and free electrons. These electrons are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards this sea of mobile electrons. These free and mobile electrons are responsible for high electrical and thermal conductivity of metals. When an electric field is supplied, these electrons flow through the not a network of positive ions. Similarly, when heat is supplied to one portion of the metal, the thermal energy is uniformly spread throughout by three of free electrons. Another important characteristic of the presence of free electrons in them, metals are highly malleable and ductile. Covalent and network solids. The wide variety of crystalline solids of non-metals result from the formation of covalent bonds between the adjacent atoms throughout the crystal. They are also called giant materials. Covalent bonds are strong and directional in nature. Therefore, atoms are held very strongly at their positions. Such solids are very hard and brittle. They have their extremely high melting points and may even decompose before melting. They are insulators and do not conduct electricity. Diamond and silicon carbide are typical examples of such solids. Also, graphite also belongs to this class of crystals, but it is soft and is a conductor of electricity. Its exceptional properties are due to its typical structure. Carbon atoms are arranged in different layers, and each atom is covalently bonded three of its neighboring four atoms in the same layer. The fourth valence electron of each atom is present between different layers and is free to move about. These three free electrons make graphite is a good conductor of electricity. Different layers can slide one over the other. This makes graphite a soft solid and a good solid liquid lubricant. The different properties of four types of solids are listed in table 1.2. Different types of solids: molecular solids, nonpolar, polar, hydrogen bonded, ionic solids, metallic solids, covalent or network solids. You must have noticed that when tiles are placed to cover a floor, a repeated pattern of is generated if after setting tiles on floor. Now we mark point at the same location in all the tiles. Example: center of the tile and C of the marked positions. Only ignoring the tiles, we obtain a set of points. This set of points is a scaffolding on which pattern has been developed by placing tiles. Now, this scaffolding is a space lattice on which two-dimensional pattern has been developed by placing structural units on its set of points. A tile is in this case the structural unit is called basis of basis or motif. When motifs are placed on points in the space lattice, the pattern is generated. Now in crystal structure, motif is a molecule, atom, or ion. A space lattice, also called a crystal lattice, is a pattern of points representing the locations of these motifs. In other words, space lattice is an abstract scaffolding for a crystal structure. When we place motifs in an identical manner on points of place lattice, we get crystal structure. Figure 1.5 shows the motif, the two-dimensional lattice and the hypothetical two-dimensional crystal structure obtained by placing motifs in the two-dimensional lattice. Spatial arrangement of lattice points gives rise to different types of lattices. Figure 1.6 shows arrangement of points in two different lattices. In the case of crystalline solids, space lattice is a three-dimensional array of points. The crystal structure is obtained by associating structural motifs with the lattice points. Each repeated basis of motif has same structure and same spatial orientation as other one in the crystal. The environment of each motif is same throughout the crystal except for on surface. Following are the characteristics of crystal lattice. Each point in the inner lattice is called lattice point or lattice site. Each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule group or atom of or an ion. Lattice points are joined by straight lines of brink out of the geometry of the lattice. We need only a small part of the space lattice of a crystal to specify the crystal completely. This small part is called a unit cell. One can choose the unit cell is many in many ways. Normally, that cell is chosen which has perpendicular sides of strongest shortest length, and one can construct entire crystal by translationals. translational displacement of this unit cell in three dimensions. Figure 1.7 shows movement of unit cell of a two-dimensional lattice. So to construct the entire crystal structure, also unit cells have shapes such that they fill the whole lattice without leaving space between cells. The two dimensions of a parallelogram with sides of length A and B and an angle small r between these sides is chosen as a unit cell. Possible unit cells or in two dimensions are shown in figure 1.8. The portion of three-dimensional crystals lattice and its unit cell is shown in figure 1.9. In the three-dimensional crystal structure, unit cell is characterized by its dimensions along the three edges A, B, and C. These edges may or may not be mutually perpendicular. Angles between the edges alpha between B and C, beta between A and alpha A and C, and gamma between A and B. Thus, unit cell is characterized by six parameters A, B, C, alpha, beta, gamma. These parameters of a typical unit cell are shown in figure 1.10. Primitive and centered unit cells. Unit cells can be broadly divided into two categories: primitive and centered unit cell. Primitive unit cell, when constituent particles are present only on the corner positions of a unit cell, it is called a primitive unit cell. Centered unit cell, when a unit cell contains one or more constituent particles present at the positions other than corners. In addition to this, those at corners, it is called a centered unit cell. Centered unit cell are of three types. Body centered unit cell, such a unit cell contains one constituent particle, atom, molecule, or ion has its body center besides the ones that are at its corners. Face centered unit cells, such a unit cell contains one constituent particle present at the center of each face besides the ones that are at its corners. End centered unit cells, in such a unit cell one constituent particle is present at the center of any two opposite faces besides the ones present at its corners. Inspection of a wide variety of crystals leads to the conclusion that all can be regarded as conforming to one of the seven regular figures. These basic regular figures are called seven crystal systems, to which system a given crystal belongs to is determined by measuring the angles between the its faces and deciding how many axes are needed to define the principal features of its shape. Figure 1.11 shows seven crystal systems: cubic, tetragonal, orthombic, hexagonal, rhombic, rhombohedral, monocyclic, tricyclic. A French mathematician Bravais showed that there are only 14 possible three-dimensional lattices. These are called Bravais lattices. Unit cells of these lattices are shown in the following boxes. The characteristics of their primitive unit cells, along with the centered unit cells that they can form, have been listed in table 1.3. Primitive cubic unit cell has atoms only at its corner. Each atom at a corner is shared between 8 adjacent unit cells as shown in figure 1.12. 4 unit cells and the same layer of 4 unit cells of the upper or lower layer. Therefore, only 1/8 of an atom or molecule or ion actually belongs to the particular unit cell. In figure 1.13, a primitive cubic unit cell has been depicted in three different ways. Each small sphere in figure 1.13 represents only the center of the particle occupying that position and not its actual size. Such structures are called open structures, or the arrangement of particles is easier to follow. In open structures, um, Unit cell with the actual particle size and figure 1.13c shows the actual portions of different atoms present in a cubic unit cell. In all, since each cubic unit cell has atoms on its corners, the total number of atoms in one unit cell is 8 into 1 by 8 is equal to 1 atom. Body centered cubic unit cell. The body centered cubic unit cell has an atom at each of its corners and also one atom at its body center. Figure 1.14 depicts a 1A open structure, B space filling model, C and the unit cell of with portions of atoms actually belonging to it. It can be seen that the atom at the body center wholly belong to the unit cell in which it is present. Thus, in the body centered cubic cell, cubic unit cell, face centered cubic unit cell, the face centered cubic unit cell, FCC unit cell contains atoms at all the corners and at the center of all the faces of the cube. It can be seen in figure 1.15 that each atom located at the face center is shared between two adjacent unit cells and only half of each atom belongs to the unit cell. Figure 1.16 depicts open structure space filling model, the unit cell with portions of atoms actually belonging to it. Thus, in the face centered cubic unit cell, corner atoms, face 6 face centered atoms. In this arrangement, each sphere is in contact with the two of its neighbors. On the number of here nearest on neighbors of a particle is called its coordination number. And thus, in the one dimensional cubes packed arrangement, the coordination number is 2. Two-dimensional close packed structure C. In this arrangement, each sphere is in contact with four of its neighbors. Thus, the two-dimensional coordination number is 4. Also, if the centers of these four immediate neighboring spheres are joined, a square is formed. Hence, this packing is called a square. Close packing in in the two dimensions, the second row may be placed above the first one in a staggered manner such that its spheres fit in the depressions of the first row. If the arrangement of spheres in the first row is called A type, the one in the second row in different and may be called a B type. When the third row is placed adjacent to the second is in a staggered manner is also of A type. The spheres of similarly placed fourth row will be aligned with those of the second row B type. Hence, this arrangement of the AB type. In this arrangement, there is less free space and this packing is more efficient than the squares. Square close packaging. Each sphere is in contact with six of its neighbors and the two-dimensional coordination number is 6. The centers of these six spheres are at the corners of the regular hexagon. It can be seen in figure 1.18b that in this layer there are some voids, empty spaces. These are triangular in shape. The triangular voids are of two different types. In one row, the apex of triangular solids are of two different types. In one row, the apex of triangular solids are of two different types. In one row, the apex of triangles are pointing upwards, and in the next layer, downwards. Close packing in three dimensions. All real structures are three-dimensional structures. They can be obtained by stacking two-dimensional layers are one above and the other. In the last selection section, we discussed close packing. in two dimensions, which can be of two types: square closed pack and hexagonal closed pack. Let us see what types of three-dimensional packing can be obtained from this. Three-dimensional closed packing forms two-dimensional square closed packed layers, while placing the second square closed packed layers above the first. We follow the same rule that was the second layer is placed over the first layer, such that the first layer in this arrangement exactly in this arrangement spheres in this arrangement spheres. Similarly, we may place spheres in the first layer. It's called A type. All the layers have the same arrangement. Thus, this lattice has A type pattern. The lattice on the sphere generated on the is the simple cubic lattice, and its unit cell is the primitive cubic unit cell. Three-dimensional close packing from two-dimensional hexagonal close packed layers, three by placing layers one over the other. Formula of a compound and number of voids filled. Packing efficiency in HCP and CCP structures. Efficiency of packing in body-centered cubic structures. Packing efficiency in simple cubic lattice. Types of point defections. Electrical properties. Conduction of electricity in metals. Conduction of electricity in semiconductors. Magnetic properties. Then summary. Solid state की summary. Solids have definite mass, volume, and shape. This is due to the fixed position of their constituent particles, short distances, and strong direct interactions between them. In amorphous solids, the arrangement of constituent particles has only short range order, and consequently they behave like super cold liquids, do not have sharp melting points, and are isotropic in nature. In crystalline solids, there is long range order in the arrangement of their constituent particles. They have sharp melting points, are anisotropic in nature, and their particles have characteristic shapes. Properties of crystalline solids depends upon the nature of interactions between their constituent particles. On this basis, they can be divided into four categories, namely molecular, ionic, metallic, and covalent solids. They differ widely in their properties. The constituent particles in these crystalline solids are arranged in a regular pattern, which extends throughout the crystal. This arrangement is often depicted in the form of three-dimensional array of points, which is called a crystal lattice. Each type of soft crystal lattices are possible, which are called a breves lattices. Each lattice can be points gives location on the particles in space. Or in all 14 different types of lattices are possible, which are called Bravais lattices. Each lattice can be characterized by its edge, length, and three angles between these edges. Unit cells can be either primitive, which have particles only at their corner position, or centered. The centered unit cells have additional particles at their body centered at the center of each face, or at the center of two opposite unit cells are also into account. There are 14 types of unit cells in all, which result in 14 Brevels lattices. The close packing of particles result in two highly efficient lattices: hexagonal close packed HCP and cubic close packed CCP. The latter is also called a face centered cubic FCC lattice. In both of these packing space is filled. The centered cubic lattice. If both the packaging space is filled, the remaining space is present in the form of two types of voids, octahedral voids and tetrahedral voids. Other types of packing are not closed packing and have less efficient packing of particles, while in body centered cubic lattice 68% space is filled in simple cubic lattice. Only 52.4% space is filled. Solids are not perfect in structure. There are different types of imperfections and defects in them. Defects and line defects are common types of defects. Points defects are of three types: stoichiometric defects, impurity defects, and non-stoichiometric defects. Vacancy defects and interstitial defects are the two basic types of stoichiometric point defects. In ionic solids, these defects are now present as Frankel and Schottky defects. Impurity defects are caused by the presence of an impurity in the crystal. In ionic solids, when the ionic impurity has a different valence than the main compound, some vacancies are created. Non-stoichiometric defects are of metal excess type and metal deficient type. Sometimes calculated amounts of impurities are introduced by doping in semiconductors that change their electrical properties. Such materials are widely used in electronic industries. The solids show many types of magnetic properties like paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism. These properties are used in audio, video, and other recording devices. All these properties can be correlated with their electronic configuration and structures. सो यहाँ पर समरी ख़त्म होती है सॉलिड स्टेट की, जो कि है 12th क्लास का केमिस्ट्री का हमारा चैप्टर सॉलिड स्टेट, जिसमें हमने पहले से देखा। सॉलिड स्टेट में हमने पहले से देखा सॉलिड स्टेट फर्स्ट यूनिट है हमारा, जिसमें हमने जनरल कैरेक्टरिस्टिक्स ऑफ सॉलिड स्टेट देखा, अमॉर्फस एंड क्रिस्टलाइन सॉलिड्स देखा। उसके बाद द डिस्टिंक्शन बिटवीन क्रिस्टलाइन एंड अमॉर्फस सॉलिड्स। उसके बाद क्लासिफिकेशन ऑफ क्रिस्टलाइन सॉलिड्स, मॉलिकुलर सॉलिड्स, आयनिक सॉलिड्स, मेटालिक सॉलिड्स, कोएलेंट crystalline lattices and unit cells, a primitive and centered unit cells, the primitive cubic unit cell, body centered cubic unit cell, a face centered cubic unit cell, formula of a compound and number of words filled, packing efficiency in HCP and CCP structures, efficiency of packing bodies, centered cubic structures, packing efficiency in simple cubic lattice, calculations involving unit cell dimensions, types of point defects, electrical properties, conduction of electricity in metals, conduction of electricity in semiconductors, magnetic properties, then summary। सो ये वीडियो बहुत ज़्यादा बेनिफिशियल होगा आपके रिवीजन में, जो कि 12th क्लास का चैप्टर है केमिस्ट्री का। एनसीईआरटी का वन शॉर्ट सीरीज हमने स्टार्ट की थी, जिसमें हमने 11th क्लास के पूरे चैप्टर कवर अप किए हैं केमिस्ट्री के, और उसके बाद हमने 12th क्लास की केमिस्ट्री स्टार्ट की है। सो थैंक यू सो मच फॉर वॉचिंग। प्लीज़ लाइक शेयर एंड सब्सक्राइब।